And not only did he create this blended model, but he also tracked an extra variable. So he blended the K epsilon model and the K omega model, and he tracked Reynolds, just one component of Reynolds stress. Why? Because that's what Johnson-King did. And so he added the minimal amount of computational work to capture the benefits of K epsilon, K omega, and tracking Reynolds stress. And that's what I view today, and what I love to use in my own research for, I guess, the last 15 years, is the Menter shear stress transport model. And it's named after Florian Menter. And here's one of the original publications, which was a NASA Technical Memorandum, TM, in 1993. And let's just look at the creator, Florian Menter. There he is. So I'll just read this for the class. This was actually published by ANSYS, so he's still like a chief scientist at ANSYS. He's out in Germany, I believe. And if you go to AAA conferences and stuff like that, go to Europe, some of their conferences, you can run into him. And he has a lot of really interesting things to his name. Obviously, he got started in federal government research, and then he transitioned to industry. And right here, here's just a few things that he probably approved in this public biography from the ANSYS website. Some of these are zonal, so we're going to talk a little bit about the zonal method. We're probably not going to talk about scale adaptive simulation. He did LES, and people also combine this model with LES. So when you combine a RANS model with LES, you get something called detached eddy simulation. So where you have steady flows which are not separated, for example, you would solve the RANS equations. These are really great at resolving shear layers and boundary layers. And where you have separation or like say jets or wakes, you would solve an LES and do a large eddy simulation. So you're using the advantages of LES where you have highly time varying unsteady flow, and where you have sort of what would be stationary flow that's attached, or in high speed shear layers, like boundary layers or shear layers from jets, you would have RANS. And maybe next week we can touch on that quick. We'll have some pictures of this before we finish two equation model. Anyway, that's his picture right there from the ANSYS website, so I borrowed that. So hopefully I'm not gonna get yelled at by the ANSYS company. And let's talk about, at least in the next few minutes of class, I guess we have maybe 10 or 12 minutes, some of the starting point of this. But in the big picture, let's just talk about the vision so we know where we're going. You're going to take K epsilon model, and you're going to try and modify it and combine it with K omega model. And you're going to kind of like try and solve one model in the outer part of the flow field, in the outer part of the boundary layer and the free stream, and solve the K omega model near the wall. Why? Because in their experiment and assessment of these two models, K omega was performing, like the Wilcox K omega model, is performing really well near the wall, and K epsilon model was performing really well in the free stream. But what happens in between? Well, not sure. So the idea is to use a blending model, which would be called the baseline model, BSL, and that's where we have a single function called f1, and f1 just varies from 0 to 1 and blends the two solutions together empirically. Okay? So that's the baseline model. Then you say, okay, well, this works great, but what if I have like separation in the flow and I want to predict that correctly? I would want to track Reynolds stress. And so when I take the BSL model and track Reynolds stress, then I get the shear stress transport model. So Menter's SST model, when you run it in a code, you're actually doing all this and solving these equations automatically. And this was all motivated, when you talk about motivation, the need to predict aeronautical flows, because they were in aerospace, and they saw advantages, right, of K epsilon and K omega, which is great. And they want to combine them and minimize their disadvantages. And they also wanted to use the Johnson-King model to predict separation and other adverse pressure gradient effects. So those were major goals and motivations. But the problem is this Johnson-King model is, of course, algebraic. And it needed to sort of be updated in the framework of a general Reynolds stress model for unstructured grids. As I noted already, K omega is more accurate than K epsilon near the walls, and people like to use that for near the wall resolving, but unfortunately it fails. Both models are really failing for pressure-induced separation. The disadvantage of the omega model is that in the free stream, it doesn't handle low values of specific dissipation well. And so we want to use K epsilon away from walls in regions of low turbulence. And so to combine the two, like the first step is to blend them. And they call these blending functions, and one might be F1 in his nomenclature, and it should just vary between 0 and 1. And so you can kind of imagine, I'll draw it instead of writing, because that's a little more entertaining for everybody. I like drawing too. Another failed artist. Near the wall of K omega, and out here we have K epsilon. And how do you blend them? Well, we have a function F1. And you can have F1 being 0 and 1 at the wall, or vice versa away from the wall, but it should go maybe, as for instance, we can choose it goes from 0 to 1. And we would multiply some function like F1 times the K epsilon equation and 1 minus F1, and we'll show this in equations in a bit, times the K omega equation. So we might do F1 out here and 1 minus F1 in here for K omega, K epsilon. So once you do that, once you create these blending functions and multiply your equations, then we somehow have to track say Reynolds stress. And we're not going to write Reynolds stress as like tau ij. We're only going to track one component, which they call, in his model, the principal component, which is the value of 1, 2. So if you form it in 2 dimensions, it makes sense to track 1, 2. That's called the principal component of the Reynolds stress. And in the original formulations of the Menter SST model, that's shear stress transport. That is exactly what we would create a transport equation for, and they've already been developed, but we'll try and simplify that down to only the physics that we absolutely need. So you can see the whole model is really dependent on 3 things, right? The K epsilon model, the K omega model, and a Reynolds stress model. But you're not doing full Reynolds stress models because we're just using the principal Reynolds stress like Johnson-King. So I'm not a genius in the field of turbulence, but I would say Florian Menter is. And this is his quote about the 2 problems I discussed. And I'll let you kind of read that on your own. So in the interest of time. And here's the second problem. And I've already talked about some of the major notes about this model. So let's, I think because it's 133 here, before I kind of get into the model formulations of multiplying F1 by K omega and 1 minus F1 by K epsilon, we'll just break here till Tuesday, because it's going to take me longer than 5 or 7 minutes to get through the model. And I think it's really important because this is the workhorse model today of industry for design. Okay, so we'll see each other Tuesday.